Have you ever really stopped to think about electricity and magnetism? I mean, they seem like totally different things, don't they? One powers your phone, the other holds a note on your fridge. But what if I told you they're not separate at all? That they're actually two sides of the very same coin, fundamentally tangled together? Well, today we're going to pull back the curtain and see that invisible link. So, let's just start with this question. We all know that if you run electricity through a wire, it can get warm, even hot. That's a pretty common effect. But here's the real kicker. Could that same current also be creating a magnetic field? Could a plain old wire, just by having electricity flowing through it, suddenly start acting like a magnet? Let's find out. You know, the story of how we first figured this out isn't some tale of a genius meticulously planning an experiment. Nope. It's a story about a total accident, a moment of pure chance in a classroom that would completely rewrite physics, and honestly, build the world we live in today. And this is the guy right here, Hans Christian Ørsted. So picture this, it's 1820, he's in the middle of a lecture, and he just happens to notice something odd. Every time he switched on an electric current, a compass needle nearby would twitch, just a little flick. It was a complete accident, but that tiny observation was the spark that ignited our entire understanding of electromagnetism, leading to, well, everything from radio to the internet. And this was it. This was the moment. For the very first time, someone had real, solid proof that electricity and magnetism weren't two separate forces. They were connected. An electric current could create a magnetic effect. That one simple fact, it changed everything. Okay, so Ørsted saw the effect of this force. He saw the compass needle move. But what does the force field itself actually look like? I mean, it's invisible, right? Well, it turns out you can actually see its shape, and all you need is a little bit of iron. You've probably seen this classic experiment. You just take a regular bar magnet, you put a piece of paper over it, and then you sprinkle some iron filings on top. At first, it's just a random mess. But then, you give the paper a gentle tap, and bam! The filings snap into this beautiful, perfect pattern of lines and curves. You're not just looking at iron filings anymore. You are literally seeing the shape of an invisible force. That pattern is what we call a magnetic field. It's the zone around a magnet where its influence can be felt. And those lines that the iron filings traced for us, we call those magnetic field lines. They're like a perfect map of this invisible energy. And what's really cool is that these lines follow a very strict set of rules. They always form closed loops. They flow out of the North Pole and curve around into the South Pole on the outside, and then continue right back through the magnet from south to north. And see where the lines are bunched up real tight? That's where the field is strongest. Oh, and one more thing. They can never, ever cross each other. Okay, so a bar magnet has its signature pattern. We've seen it. But what about the magnetic field made by electricity, the one Ørsted found? Does it have a signature? You bet it does, and it follows its own set of rules. So, unlike the big, swooping arcs of a bar magnet, the magnetic field around a straight wire with current is actually much simpler. It forms these perfect, concentric circles, kind of like ripples in a pond, with the wire sitting right in the middle. And get this, there is a super easy way to figure out which way those circles are spinning. It's called the right-hand thumb rule. Go ahead, try it. Imagine you're holding the wire in your right hand. If you point your thumb in the same direction the current is flowing, the way your fingers curl around the wire, that's the exact direction of the magnetic field. It's a fantastic little life hack for physics. Now, what makes this field stronger or weaker? Well, it boils down to two really simple things. First, if you crank up the current, you get a stronger magnetic field. Makes sense? And second, just like you'd guess, the farther you get from the wire, the weaker that field becomes. Simple as that. But this is where it gets really clever. What happens if you take that straight wire and you wind it into a coil? Something awesome happens. All those little circular fields from each loop, they all add up and reinforce each other, creating this much stronger, much more focused magnetic field right down the middle. And in fact, a coil with a current flowing through it behaves almost exactly like a bar magnet. That's what we call an electromagnet. So we know electricity can make a magnetic field. Cool. But this is where the relationship gets even more wild, because this isn't just about invisible fields anymore. Now we're talking about creating real physical force, real motion. So let's set up another little thought experiment. We've got our wire, and it's carrying a current, so it has its own magnetic field circling around it. Now, what do you think would happen if we took that wire and put it inside another magnetic field, like between the poles of a strong horseshoe magnet? Now you've got two magnetic fields trying to occupy the same space.
Well, those two fields interact. They push and pull on each other, and the result is a real physical force on the wire. The wire literally gets kicked, pushed, or pulled. And that one simple concept, that is the fundamental principle behind basically every single electric motor on the planet. From the thing that makes your phone vibrate to the engine in an electric car, it all comes down to this: using magnetism to push a wire.
And yeah, you guessed it, there's another hand trick to figure out which way the wire is going to get pushed. This one's called Fleming's left-hand rule. So with your left hand, if your forefinger points in the direction of the magnetic field and your middle finger points in the direction of the current, then your thumb points in the direction of the resulting force or motion. It's this perfect three-way relationship. And this principle is absolutely everywhere. It's not just in motors. It's how loudspeakers use a magnet and a coil to vibrate and create sound. It's how microphones work, just in reverse. It's even how old-school analog meters move their needles. This dance between electricity and magnetism is a cornerstone of our entire technological world. Okay, let's bring all this theory right back into your house, because these exact same principles are at work 24/7 inside your walls, both powering your life and keeping you safe. In a lot of countries, the electricity that comes into your home has what we call a potential difference of 220 volts. You can think of this as the electrical pressure that's ready to push the current through your lights and appliances. And that power usually gets delivered by a team of 3 wires. First, you've got the live wire, typically in red, which carries that high electrical potential. Then there's the neutral wire, in black, whose job is to complete the circuit. And finally, you have the green earth wire, which is a really, really important safety feature. See, that earth wire, along with things like fuses, is there to protect you. If something goes wrong, say a live wire accidentally touches the metal case of an appliance, the earth wire gives all that dangerous current a safe path to the ground, preventing you from getting a nasty shock. It's a super practical application of controlling how electricity flows. But maybe the most incredible electrical circuit of all isn't in your walls. It's inside of you. The tiny ion currents that travel along your nerves, your thoughts, your heartbeats, they also produce magnetic fields. Now, they are ridiculously weak, something like a billionth the strength of the Earth's magnetic field. But the fields from your heart and your brain are just strong enough that we can actually measure them. That is the very principle behind technologies like MRI scans. So think about that. This invisible link between electricity and magnetism isn't just something out there in power lines and motors. It's in us. It's part of what makes us tick. Which kind of leaves you with one final big thought. If our own bodies are fundamentally electromagnetic, what other invisible connections that shape our entire universe are still out there, just waiting for us to discover them?